Techme from B-Town, Ontario asked, is it challenging to brush your teeth in space without getting toothpaste up your nose from weightlessness? Well, let's talk about how to brush your teeth in space. Standard toothbrush, nothing magical there. But we got a few different things. We don't have running water. You can't have a tap. You can't have a sink because water would flow everywhere. And so what do you do to wet your toothbrush, and where do you spit afterwards? Those are the big questions. So first we just fill up a water bag with water, and this is what we're going to put on our toothpaste. So let me get a ball of water here. There's a nice ball of water floating on the end. Shut off the straw very carefully. Okay, and get my toothbrush wet. Toothbrushes soak up water nicely. So now I have a nice wet toothbrush. Good. So I'm partway there. Got my toothbrush wet. Now I just need to put some toothpaste on it and get cleaning my teeth. So I'm going to suck the water off it because where else would it go? Nice wet toothbrush. Grab some toothpaste. We just use standard toothpaste in space. Squeeze a little on, not too much because you're going to have to clean it up later. Okay, so there's my toothpaste on my toothbrush. It's wet. It's ready to go. It's loaded. Brush my teeth just like normal. Get them all, especially the ones in the back. You should brush your teeth for about as long as you can sing Happy Birthday. That should be long enough. Okay, so now what am I going to do? I've got a mouthful of toothpaste stuff. I got a dirty toothbrush. So what I do is I just swallow the toothpaste. It's edible, won't kill you. And what else am I going to do? Put it in a rag and have a dirty rag? Doesn't make any sense. So in space, you don't swallow your toothpaste. It leaves my toothbrush just a little bit dirty, so I need to find where my water went and rinse it out. Fortunately, things are weightless, so things don't go too far. So here's my water again. So now I'll get a little water in my mouth. Rinse out my toothbrush. So I have a relatively clean, slightly damp toothbrush to put back in my toothbrush case. The toothpaste is hung back on the wall. We communally share one toothpaste tube, just like living in a dormitory, and I still have good water to drink. And it doesn't go up your nose. There's nothing to push it up your nose. It just floats, so it works fine. That's how you brush your teeth in space. See what happens. I'll get up close so you can see here. Oh, there's one ball of water floating around. I'll put it on the washcloth. Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. It's becoming a tube of water. It's becoming a tube of water. It looks very cool. The water's running up my hands a little bit. Hey, Tom, can you come grab me a towel, please? I got one on the wall. It's over here by Sivas. So it'd be on the other side of Sivas there, stuck in the wall. So the water's all over my hands. In fact, it wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. The surface tension of the water keeps it stuck to my hand. Thanks, Tom. Grab the microphone. Okay, so the experiment worked beautifully, and the answer to the question is the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jello on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer on my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations, great idea.
Okay. Flash. Oh. Box, move back.
That's funny.
All right.
You keep me honest because I can't see how close I am to it.
Okay. You ready?
Okay, just keep telling me.
Move back. So here we go.
You drinking it?
Nope.
It's on your nose?
Yep.
It looks like a clown nose.
And
Oh, yeah. That's kind of freaky, actually. It's kind of scary. Is that how you guys wash your face on the space station?
nope. That was the first time I did that, and it worked well.
It's kind of cool just to watch them move. Okay, there. Okay, I'm going to put a puff of air in from this side. Here we go. Wow. Cool. Wow, I just love those oscillations. Here we go. Okay. Let me switch it to a black background. Yeah, so that's about 800 mils. So this should put it around 1100 milliliters. Let's see what happens here. Oh, I just love that. Look at that. Amazing. Just one of these jaw-dropping moments. Okay, here we go to do it again, looking into the camera. Big puff. Here we go. Oh, right at the lead. I saved the lens. What I'm planning to do is, after this whole series of experiments, I'll suck all this water up with a syringe, I'll put it back in bags, and I'll use it to make tea with, so I'll end up drinking my experiment. You gotta conserve your resources when you're in a frontier. You don't get to see this as common, intuitive observables on Earth. And so when we go into a frontier, our normal Earth-honed intuition no longer applies. And this rule works when you go to the bottom of the ocean or into the stratosphere or wherever you find your frontier under the stage of an electron microscope. Your normal everyday life intuition no longer applies. And that's why frontiers are rich in discovery, because things aren't the normal, they aren't the usual. Joe, come take a peek at this.
Holy crap.
Get my towel ready to catch the satellite drop. Here we go. Isn't that wild?
That's great.
It's a superposition of surface waves that go around the outside of the sphere and body-centered waves, inertial waves that go through the middle. I'm going to give it another puff just because I'm in space and I can. And instead of putting a puff of air on it, I'm going to put a puff of water. This is going to have a lot more momentum in it than the air. Whoa, whoa, I was afraid. Oh, look at that, cool. I squirted water through. Oh, isn't that cool? The water in the sphere went around the air cavity and formed a huge bubble. Wow. Oh, that is so cool. Let's see what my hand looks like. Oh, look at that. Yeah, oh. There we go. Yeah, that's good. That's good. Shows that optics works. And let's see what my mug looks like. Oh, I can be a human pendulum. This shows the lens law. Motion is in the opposite direction and the image is inverted or upside down. And there I am, and I'm going to come up here with my eyeball. Now I'm going to do the same thing with my nose, and this is going to get ugly, and I apologize in advance. I look like I have a floating head. I have a black shirt on, and it blends with the black background, so I'm just a floating head. Okay, enough of that. And let's get back to doing some science. Oh man. It swallowed a how am I going to get those out?
Let go of much energy. That's so wild. Kind of push it in. 3, 2, 1. Oh, it made it out the other side.
A little too hard.
That is wild. There, I think it's gonna stay in now.
Yeah, but you gotta get it from going back down.
Okay. What else can we get inside there? Now you're stuck in it? You're being assimilated by the. Pull out quickly. Oh, dude.
This is gonna get worse and worse.
We film it.
Dude, this is amazing. Look at that. Whoa. Holy smokes. Oh my gosh.
That is absolutely fascinating.
common middle school experiment mixes oil and water to show that oil floats on top of the water. This happens because the two fluids are A, immiscible, that is, they do not mix, and B, different densities. A quarter cup of oil weighs less than a quarter cup of water, and so the oil sits on top of the water. Why is the oil on top? The answer is intuitive. Heavy things sink down and light things float up because gravity pulls on the heavy things harder. But what happens when the g-force goes away? Well, if we don't have a down, we don't have an up, and so who knows what'll happen. Carthage College's microgravity team explored what happened in August 2013 with some help from NASA. To figure this out, we need two things, a density tower and a zero-G environment. The first item is pretty easy to obtain, and we don't need to use only two fluids. Some enthusiastic scientists have created these density towers with 9 different fluids, and they behave pretty well as long as they aren't jostled too much. Here is a tower with 3 immiscible fluids, vegetable oil, water with blue food coloring, and some leftover FC72 we had in the lab. FC72 is an experimental spacecraft coolant. It performs the exact same job as car coolant, just in space. Links in the description for more about FC72. The zero-G environment is a bit harder to come by. Thankfully, Carthage College had been selected by NASA to perform a different experiment with FC72 in zero-G. To perform zero-G experiments, NASA uses G-force 1, the microgravity plane. To make zero-G, G-force 1 flies in a parabolic shape. That is, they go up in the air at full speed, and then cut the engines to fall to Earth before turning the engines back on, and repeating the whole process over and over again. The Carthage College microgravity team took the 3-fluid density tower aboard G-force 1 when they went to Ellington Field in Houston, Texas to perform their FC72 experiment for NASA. In the footage that follows, you'll mostly see John Robinson and Eli Favela handling the density tower. Before we get rolling with the footage, here are 3 tips for successfully coping with zero-G. Number 1. Find a nice place to lay or sit on the plane. Why? Because when the plane is catching itself, everyone experiences 2 G's of force, and so it feels like a clone of you is sitting on top of you. And it's best to take that like a rug, laying sprawled out. Tip 2. Watch your feet. Amateurs flail their feet to try to stabilize. Astronauts like Clay Anderson calmly fly above the chaos. Tip 3. The hypergravity portion of the flight is an excellent time to do push-ups and sit-ups if you didn't have time to work out because of all the science you were doing. Okay, let's turn it over to John to see the fluid in action.
Density tower. It's got different liquids, different densities. So right now we're in the hypergravity, so they're really separate. So we have FC72, water, and vegetable oil. Then as soon as we hit zero, as soon as we go into microgravity, well, you'll see. Zero. Science!
That was a bit tough to see as John started to float away with the tower, but did you see the way it oozed? Let's see it on the next parabola, once John has strapped himself down a bit.
1, 0. Not separating at all. It's just sitting there floating. All of it mixed up. Yeah, just a little bit. And then we go into regular gravity, hypergravity, and it separates out again.
Did you see how the fluid didn't separate out like it did in normal gravity and hypergravity? And did you see the different color blobs just cycle around? Watch it one last time as John swishes it up going into zero-G.
0. Science. Feels like the pump's still working. Oh, that's pretty cool swirling in there.
Tip 4. When you go to shut off the camera, make a funny face. In conclusion, when we take away gravity, we take away up and down. With no sense of direction, neatly ordered systems like our density tower start acting all chaotic, with everything going in all directions. And that is pretty cool.
К Рождеству я посылаю поздравления на станцию, и на ум мне приходят слова французского поэта: «Земля голубая, как апельсин».
I'm about to experience weightlessness for the first time.
Injection. And now you feel zero.
Oh my god. Oh my god. That is so strange.
Oh my god. Oh my god. This is totally freaky. This is way better than I expected. I'm just gonna say this right now. I'm going up to the ceiling, and here we are. I am ridiculously excited because behind me is a zero-G plane. I'm in France. I was invited here by the YouTuber Bruce. This is Bruce, Diana, physics girl. We are going, flying some parabolas. We're going into zero-G. It's gonna be awesome. Come on.
The principle behind weightlessness is pretty simple. The plane and everything inside it just need to accelerate towards the Earth at the same rate as a freely falling object in a vacuum, that is 9.8 meters per second squared. So you can think of your body as this pen and the plane as this bottle, and when it's freely falling, there's no contact force between the pen and the bottle, and so the pen feels weightless. So you might think the way to do this is just to put the plane into a dive, but that's not actually how it works.
Instead, the plane starts climbing at a steadily increasing angle. With no windows inside, it's impossible to tell that this is happening, and all you feel is pressed into the floor with a force 1.8 times your body weight. This is because the plane's acceleration is directed upwards and perpendicular to the floor, and it makes standing very difficult. Not only are you nearly twice as heavy, all the blood drains from your head and into your feet, which made me pretty dizzy.
So weak.
Lying on your back is much more comfortable, and we're advised not to move our heads around and look straight ahead, because in hyper-G, our vestibular system is hypersensitive to movement, which can lead to motion sickness, and that's why this is sometimes called the vomit comet. Once the plane is climbing at about 50 degrees, the engines are ramped down and the plane is put into a parabolic trajectory. It's at this point that you start experiencing weightlessness.
I can feel myself getting lighter. Whoa, that is such a strange feeling. That is so weird.
The plane and you are still moving upward, but you are accelerating downward.
There's Diana. She's the physics girl.
Then the plane peaks and starts speeding up again towards the Earth.
This is totally strange.
The whole time, the plane is accelerating toward Earth with the same acceleration as a free-falling object in vacuum. The pilots have to very skillfully adjust the thrust to perfectly balance air resistance and maintain exactly this acceleration.
Okay. Oh my goodness. How do you feel?
It's incredible.
So it's like throwing this bottle into the air. The pen inside experiences weightlessness from the time it leaves my hand until it comes into contact again. After 22 seconds of weightlessness, the pilots pull out of the dive, again subjecting us to hyper-G as the plane accelerates upwards. In total, we performed 13 of these zero-G parabolas, plus 1 Martian gravity and 2 moon gravity parabolas.
Okay, we are now in Mars gravity. In Mars gravity, I can do one-arm pull-ups, maybe.
Push-ups, push-ups like this. Yeah, like this. Wow.
I am the Martian.
We brought along some experiments to do in zero-G.
So this is in about 1G of gravity. This is what the flame looks like on this barbecue lighter. Now we're going to try it in hyper-G, and then we'll try it in zero-G, and it should be...
We will see.
We will see.
We take it for granted that flames have this distinctive shape, but that's only because of gravity. The products of combustion have more energy, and so move around faster and take up more space than the cooler air around them. Therefore, there's a buoyant force on them which is greater than their weight, and so hot air rises. This helps pull in the oxygen from around the flame to continue the reaction.
We're going through hyper-G. I keep blowing out the candle because the stress of hyper-G is significant.
In hyper-G, this effect is magnified, since the effective gravity is almost twice as much. This amplifies the difference between the weight of the hot air and the weight of the cooler air around it, and so the hot air rises faster, making a longer flame.
Oh my goodness. Look how that flame just wafts in zero-G because there's much less buoyant force to carry away. And so the combustion is not as good. You can see a lot of smoke coming off of that candle. That is incredible.
Hey, Derek.
Hey!
So we still have a gas flow, so this is why the flame is not circular.
It still goes up because...
It is not a sphere, but it looks very strange.
In zero-G, the hot air is still less dense than the cooler air, but now there is no weight and no buoyant force. So the flame doesn't rise as high. This flame still maintains some of its shape because of the flow of fuel from the lighter. Otherwise, the flame would form a sphere, like on the space station, where it's very difficult to maintain the combustion reaction because it's hard for oxygen to access the fuel with all of the combustion products getting in the way. So if you're ever unsure about what the gravitational acceleration is where you are, well, looking at a flame is a pretty good way of finding out.
I want to say a huge thanks to the team at Novaspace who made this an unforgettable experience, and of course to Bruce, who runs the French YouTube channel Y Pensez, for inviting me. You should really go check out his video from the Zero-G experience, and of course Diana, the physics girl, go check out her video on Zero-G here.